So yesterday we talked about geodesics in Kerr spacetime, and we started to map out this parameter space in terms of the energy and angular momentum, which are the conserved quantities along these Kerr geodesics. In particular, we looked at this sort of dividing line in the space of E and J that's set by circular orbits. And on either side of that space, we may have bound orbits or just have orbits that fall into the black hole. And we classified those circular orbits into stable ones and unstable ones. And then hopefully yesterday afternoon, you sort of got a more intuitive feel for what these geodesics look like in Kerr spacetimes by actually integrating the geodesic equations and looking at cases, in particular these zoom whirl orbits. So to begin with, today I want to talk a little bit about a different class of Kerr geodesics, and that's marginally bound orbits, which are in Newtonian theory called parabolic orbits. So these are the ones where we're in the dividing line between the ones that can not escape to infinity and those that can, or equivalent those that come in from infinity or those that have to come in from some finite radius. That's just given by, as we discussed yesterday, where the normalized energy is equal to 1. So, in Newtonian theory, these are actually parabolas, but in our Kerr spacetime, we get this precession. So, we can get things that look like that, or, as you found yesterday, you can have lots of whirlings and then go back out. So, if you look at the expression we wrote down for this effective potential for geodesics yesterday, you'll notice it has these terms that are like, 1 minus E or 1 minus E squared. And so the potential actually simplifies very nicely in the case where E tilde is equal to 1. In that case, it just becomes this expression. So in particular, we used to have our cube term here, but its coefficient was like 1 minus E tilde squared. So we now have one lower term polynomial here. So in particular, we can, again, we're interested in the turning points. And that's where V is equal to 0. So we don't have to solve any cubics or quartics. We can just solve this quadratic to determine where this is equal to 0. And I'm going to call this radius where it's equal to 0 RP for the periapse radius. That's just all over 2. So just a quadratic equation. And so, since we have this quadratic equation and V, and you recall yesterday that we showed that at R plus, this is negative. And then we can see that again at very large R, this is also going to be, this term will be dominant times this. So we'll also have a negative value. So we know that our potential is going to be negative at R plus, and also at infinity. And then in between, we have 1 or 2 options for zeros. I can either cross, and we get 2 zeros, or we can have no zeros, something like that. And so, the dividing line between these two cases is just going to be when this discriminant vanishes. So let's solve for the value of the angular momentum j where that happens. We get something like this, where I've just kept only one of the roots. So we can take this value for j and then plug it in here. So remember, we just chose the case where this is 0, so we just get that first term divided by 2, and then plugging this in. We arrive at this expression. So this is basically telling us the radius at which this marginal case happens. It's the dividing line between orbits where we can come in from infinity, we go to a finite value, and then we go back outwards, versus just coming in from infinity and falling all the way to the black hole. Any questions about that?
In your quadratic formula there, should that be like j tilde to the 4 over 4m squared?
Oh yeah, sorry, yeah. Thank you.
Would the a above be squared?
Here? I think that's right.
Shouldn't it be symmetric on the change?
Well, so I chose one root, so yeah, so this is, yeah, I mean, we'll look at this at both the case where a bar is prograde or retrograde, but I've chosen this to be positive, which is our convention last time. Yeah, that's why we could choose one root. Yeah, so. Yeah, so basically any of these parabolic orbits with, yeah, they go less than this value will plunge right into the black hole. Yeah, so let's look at this for a couple different cases. So in the retrograde case, there we get three here, and then 2 times the square root of 2. So that's about 5.8. Can look at the non-spinning case. So we get 0 and then 2. So that's 4. And we can look at the prograde case. And there we get -1, and this goes to 0. So we just get m. So you can see that for any non-extremal value of the spin, this periapse value is going to be less than the equivalent ISCO value. And in fact, this is the minimum value. This bound holds for any bound orbit, because we can we can get closest to the black hole in the case that we have the most energy allowed while still being sort of marginally bound. Yeah, so just a brief comment about how this might give us some intuition for an astrophysical scenario. So one thing that astronomers sometimes see are these bright flares that they think are coming from the supermassive black holes around centers of galaxies and are due to something called tidal disruption events. So the idea is you have a supermassive black hole. It's a black hole that has something like 1 million or more times the mass of the sun, and you have some population of stars that is interacting, and at some point, in some instances, some of it will get kicked out onto an orbit that'll go close to the black hole. And so if we think of these stars as having, very low velocity compared to the speed of light at infinity, and then coming close to the black hole where their speed is comparable to speed of light, we can basically, ignore the velocity in infinity. It's going to be very small and treat it as just a marginally bound orbit. And so when the star gets close to a black hole, it'll experience tidal forces. Basically, the gravity that the side of the star that's closer to the black hole feels will be greater than the part of the star that's farther away from the black hole. And if this tidal force becomes significant enough to overwhelm the self-gravity of the star, you have what's called tidal disruption, where the star will get pulled apart and basically sort of move more like a cloud of dust or something like that. That's just where the motion of the star's fluid is determined by the black hole's gravity. And then this material can fall back and form an accretion disk and accrete into the black hole and power these bright flares that astronomers see. So in order for this to happen, we want the star to get close enough to the black hole where the tidal forces are strong enough to pull it apart. So this sort of depends on the relative size of the star compared to the black hole. But we also don't want an orbit that just falls straight into the black hole, because then even if the star is getting pulled apart, it'll all just rapidly fall into the black hole and won't have time to form one of these accretion disks. So given that story I just told you, what would you think the effect of black hole spin would be on whether or not you could get a tidal disruption event for a given star? So if the star is too small compared to the black hole, it won't be tidally disrupted unless it gets very, very close to the black hole. But if we treat the star as spinning versus non-spinning, how would that enhance or change basically the size stars that you could tidally disrupt based on what we just talked about here? Anybody?
I think if the star's spinning really fast, then on average it's not gonna get affected much by the tidal force.
Sorry, say that again?
I would think that if the stars are spinning really fast, then
Yeah, sorry, I'm interested in what happens with the spin of the black hole.
oh,
Yeah, if we change the spin of the black hole, how does that change this tidal disruption picture? Or like the given stars we could disrupt without having them fall right into the black hole?
Well, it depends on the orientation of the spin.
Yeah, so what would happen if the
So if they are,
orbital angular momentum is aligned with the black hole spin?
if they are aligned, you get more disruption events. If they are anti-aligned, less.
Yep, exactly. Yeah, because we can have parabolic orbits that basically go closer to the black hole and therefore experience a greater tidal force without actually falling into the black hole than in the cases where we don't have this black hole spin. Yeah. Yeah, so we can also notice from this equation that let's say we want to have a parabolic orbit that comes into the black hole's ergosphere. When does that happen? So you'll recall that the ergosphere is at 2m in the equator. And so if we just use that expression in here and solve for A, you actually get that we have to have quite a rapidly spinning black hole where the dimensionless spin satisfies this equation. And again, just if you solve the quadratic, you get this fact. So if we have a black hole with this dimensionless spin of greater than 0.91, we can actually have these parabolic orbits that enter the black hole's ergosphere. So that's a nice transition to the next topic, which is how we can actually exploit the black hole's ergosphere in order to tap into a black hole's rotational energy. So this idea is actually due to Roger Penrose. So this is a Penrose process. And in the next couple classes, we'll talk about sort of many different versions of the story. But this is the one with you can do with sort of putting together geodesics. So to begin with, let's just remember that the forward momentum of a given observer is given, let's call it PA, is just the forward velocity times the rest mass of that particle. And the energy that this particle is seen carrying is observer dependent. So if we have some observer with forward velocity NA, then the energy that observer NA will see is just given by the contraction of the observer's forward velocity with the momentum of the particle. And this energy will always be positive as long as this forward velocity is time-like. However, this observer-dependent energy is not the one that's actually conserved along geodesics, right? The conserved one is the one we get by contracting with the killing vector, our killing vector that's time-like at infinity. And as we discussed in previous classes, this vector actually becomes space-like in the ergosphere. And so it is possible to arrange for this to be negative. So whenever you see that you can have some energy that's negative, you can kind of think of that as, that might lead you to think that we can somehow gain energy out of this system by creating, still conserving energy, but by creating some negative energy and then getting some positive energy to balance it out. But we can only do this sort of in the ergosphere. So that led Roger Penrose to suggest the following scenario. So let's say that you have, you're on a long space voyage, you're in your spaceship, you're running low on fuel, and you see a rotating black hole nearby, and you want to use it to try to gain some energy. So let's say you point your spaceship towards the black hole with some initial form momentum, we call it PA. Okay, and then you choose this forward velocity, your forward velocity basically, so that you'll enter the black hole's ergosphere. So then once you're in the black hole's ergosphere, you take all your garbage and recycling, all your mayonnaise jars, all those beer cans you meant to take to the beer store but never had time to, and you toss them out of your spaceship into the black hole. And so we can basically, we're still going to require that we conserve momentum and energy, but we'll divide basically our incoming forward momentum into two components. One is part that's our spaceship that will escape the black hole vicinity, and then the component with all our recycling that will fall into the black hole. And in particular, we want to arrange that the energy carried by all our recycling, which is, of course, just this quantity, is going to be negative. And so, in particular, if I contract this equation with the t killing vector, we just get conservation of energy. So that means that the energy carried out by our spaceship is the initial incoming energy minus this negative quantity. So it's going to be actually greater than our incoming energy. So we're going to gain energy by doing this process.
So what you would do inside your spaceship is grabbing the garbage and throwing it in some direction?
Yeah.
Then you would go to the other one that conserves the momentum with more energy, presumably?
Yeah, so so basically we'll work through an explicit example of this in just a second. But yeah, the basic idea is that you have some incoming geodesic, then you reach some point, and now you're going to have some process that basically conserves energy and momentum but splits it into two different objects.
Okay.
And so then you'll have basically two different geodesics that will be followed by these two different components. But the total momentum and energy at this sort of, you can think of like the explosion point, or when you sort of exert some force to toss something out of your spaceship, is zero. So you're still conserving energy and momentum at that point. Yeah.
Right, but you have to invest energy in order to throw your garbage away, right?
Because it should be a geodesic.
I mean, yeah. I mean, you're still conserving energy. I mean, we're still assuming that when you go from this form momentum to the two different ones, the total energy is still the same, right? Yeah.
But I mean, if I were just to split up my spaceship into two parts, they would move together. So I have to create some delta V between them, right?
Yeah. So yeah, you need some sort of explosion or something like that. Yeah.
Okay, and I guess we're going to see that this energy required is less than the energy we gain.
Well, I mean, we're not going to really talk about that. Like this process in which you would actually go from this form momentum to these two different ones. But I mean, you can see this does satisfy energy conservation, right? But it's just, but we're not going to go the mechanics of actually, taking one object and splitting it into two or something.
Internal energy that you're spending, though. I mean, the kinematic one, okay, that one, you get more kinematic, but at some point you have to boom, and that boom is internal energy that is not considering to that.
You might consider that you have to, have some sort of internal energy that gets converted to some other kind of energy or something, but still the total energy will be conserved, right?
Okay.
Yeah. So we want to see if we can actually arrange for some specific set of geodesics that will satisfy these equations, and also see, what's the sort of maximum efficiency you could get out of this kind of process. So for the specific example, let's again focus on these parabolic orbits we just talked about. So I want to assume that E tilde is equal to 1 for our incoming particle. And we'll actually set the mass of the incoming particle just to 1 for convenience. And as I mentioned before, let's assume the spin of the black hole is sufficiently large such that these parabolic orbits can actually enter the ergosphere. Okay, so the incoming forward momentum will be given by this expression. So basically, we're going to consider this parabolic orbit at its turning point. So this, we're going to do this split where we throw out our recycling and then power on with our spaceship at the turning point where the radial velocity is equal to 0. So we just have this azimuthal component to velocity, and then since I set m equals to 1, this is basically the same as the forward velocity. And then this omega, just by definition, is going to be d phi d tau divided by dt d tau. So it's just sort of our coordinate omega. And this quantity here we can, of course, calculate just by normalization. So using the fact that this should equal minus m squared, which in this case is just minus 1. And let's call this equation star, so we can use it later. So if we also use this fact here, that E tilde is equal to 1, which is just the same as the energy for this m equals 1, and these m equals 1 units. Plugging in our expression for the energy, we get this. So I just divided the expression for energy by minus dt over d tau. And let's call this equation double star. So we can just combine those two equations. Star and double star to get an expression for omega. So combining those two equations. So again, we get a quadratic equation for omega that we can solve, but won't write down the expression. Okay, so now let's turn to the two particles that we're going to split this form momentum into. So so we have our incoming spaceship with the recycler, we split it up into recycling and the spaceship at the turning point. And in general, we could have some radial momentum to each component as long as they basically add up to satisfy energy momentum conservation. But it'll actually turn out that adding some radial component to either will reduce the efficiency. So for now, let's just focus on the case where, again, neither has a radial component instantaneously at this point. Though, of course, there will be some sort of radial acceleration, and when this guy will go out to infinity and this guy will fall into the black hole. And here I've just introduced these constants CR and CS, and of course those are just equal to dt, d tau for the individual objects times the rest masses of the individual objects. So if we just write down conservation, this basically gives us two equations because we have two sort of non-trivial components to these. And writing down those two equations, from the time component, we get this. And from the phi component, we get this. Okay, and so we have two equations. We can just solve for CR. Actually, we can solve for. Actually, can use this equation to eliminate CR from this equation and then solve for CS. And so we get first and then solving for CS, we get okay, any questions so far?
I have like, what's the little subscript in the definition of CR? You have dt tau and you have a subscript there. What's?
Oh yeah, this is just the rest mass of
No,
the.
I mean, underneath the derivative.
Oh, here I just.
What's that?
This is just indicate. This is dt tau for the recycling. So
yeah.
when I say dt tau here, I meant it for the original incoming system. Okay, so now we're ready to calculate the energy for our spaceship that escapes to infinity. So the energy is just, again, we contract with the time-like killing vector. So we just get a GT component times 1, and then a GT phi component times omega. And then using this expression for CS, we can eliminate that from this equation.
That's supposed to be PS rather than PR?
Yes, that is. Thank you. Okay, so yeah, and here, you know, if we just use that expression, we also get something involving dt d tau, but then hopefully I didn't erase it somewhere. Maybe I did erase it, but
The question 2 on the upper right to start.
yeah, where is it?
On the upper right is Blackboard.
Oh yeah, yes. You can still see that up there, yeah. We're using this 2-star equation to eliminate that from this as well. And then we get this answer here. So this is the energy we're escaping to infinity with. And so we can use this to calculate the efficiency of our extraction. But the thing we haven't done yet is to figure out what velocities we want to take, sort of what rotational velocities we want to take for our spaceship and our recycling. So to sort of see the limits of that, we can look at this normalization constraint. Yeah, so up there again, equation star. So basically, if we assume that the form momentum is time-like, then it has to satisfy this normalization constant. But you can see that we have this quadratic equation on omega in equation star. And basically, the zeros of that equation will determine the limits that we can take for omega. 1 0 will be the minimum, and 1 0 will be the maximum. So let's solve that equation. So just the term in parentheses in equation star, setting that to 0 and solving for omega. We get this. We can just cancel out the 2's. And basically, so I'm calling these two different roots omega plus and omega minus. And so basically, what we're going to have is that both the rotational velocity of our recycling, which we want to be bigger than that of our spaceship, both of these quantities have to lie in between these two values in order to give us time-like form momentum. So this is just basically the limits of the light cone. So we can think of when we choose omega equals to omega plus, we're sort of on one side of the light cone moving at the speed of light, and omega equals omega minus. That's also gives us a null velocity, but the minimum one. So we have to lie in between here. But if we actually want to minimize the efficiency of this process, we basically want to take the limit where this goes arbitrarily close, where omega s goes arbitrarily close to omega plus, and omega r goes arbitrarily close to omega minus. So if we take those limits, let's just look at a particular case as well where we can simplify things by letting the spin go to extremal value. And so again, this is actually where you get the most energy, as you can imagine. The ergosphere is the biggest and the black hole is rotating the fastest. And then we want to look at the efficiency, which is basically just ES, which we have this quantity here, minus our incoming energy divided by the incoming energy. But by our convention, this is just 1. So basically, we have all the formulas we need. We just need to plug in the expressions for the metric of our Kerr metric, and things will simplify somewhat in this extremal case. So I won't bother to actually go through all that algebra, but we can just plot what these look like. So for omegas, so I'm going to plot this in units of the horizon frequency of the black hole. For the extremal case, this is just 1/2m. So this is for the extremal case. So basically, we can see what happens as we let the radius. So basically, for the turning point of our parabolic orbit, we can choose different values of the radius, right? For the extremal case, the periaps can actually go all the way, arbitrarily close to the horizon. So we can choose the value for our turning point in between r plus and the outer edge of the ergosphere, which occurs at 2m, and just calculate what these quantities look like there. And we get this behavior for omega minus, starts at 0, and then goes to omega h. And this value for omega plus. And of course, omega, the rotational velocity of our incoming particle at its turning point, has to lie in between. And yeah, so you can see basically we have some sort of singular limit here as we go to the, as we let r go to r plus in the horizon where these sort of all three meet. However, if we look at the efficiency, eta, as one might imagine, is actually 0 at 2m because we're just barely coming into the ergosphere. But then actually is monotonically increasing, and then at r plus it actually reaches this value of about 0.21. It's actually square root of 2 minus 1/2 if you work through all the algebra. So for this limit where r goes to r plus, you have to be careful because you notice these are all going to the same value. So in this expression here, we're basically going to get 0/0, but we do still get a finite limit as we sort of let our parabolic orbits go closer and closer to the black hole horizon. So this is sort of the maximum efficiency you can get for one of these marginally bound orbits that comes in from infinity. And if we added some radial velocity or something like that, that would basically reduce the values of omega r and omega s that we could choose, because there would be some additional velocity component that would prevent us from allowing this large omega while still being time-like. So any questions about that?
Yeah, I have a question for me. For how did we use the equation star to get the omega plus and omega minus? I lost that part. Because we have that equality equals -1, but we're making 0 the...
So that expression, in star we have this like dt tau squared times this other term.
Yep.
And so if that term becomes 0, then we can't choose any value of dt d tau such that we get -1, right? And basically the problem is we now have a null form momentum instead of having time-like form momentum.
Okay.
So basically that's why, to have a time-like form momentum, we need to choose a value of omega that lies in between omega minus and omega plus. So we can't actually set omega r and omega s exactly equal to these things, but we can get arbitrarily close.
Okay.
Any other questions? Okay, so now let's go back to talking about these particle processes in general. So you'll recall this vector that we called chi. That's just given by this linear combination of our time-killing vector times omega h, the horizon frequency of the black hole, times the axial killing vector. And so this killing vector is actually time-like as long as you're outside the black hole horizon, and then it becomes null on the black hole horizon. And so that means that any object that falls into the black hole, if we contract its form momentum with chi, we should get something that's less than 0, just by our energy condition. Negative. This would be the energy. Which we want to be positive, and then we're basically taking the limit you get close to the black hole where this becomes null. So if we work through what this means for, so just using this definition of chi and contracting with this, we get basically from this term, we get the minus the energy that the particle carries, which I'll call delta E, just its conserved killing energy, and then get omega h. And then from contracting this with the form momentum, we get its conserved angular momentum, which I'll call delta J. And so this has to be less than 0 for any particle that enters the black hole horizon, and in particular for any particle we construct by such a like a Penrose process where the energy is negative, this still has to hold. So if we have a negative killing energy particle, that means that we have the delta E, which is less than 0, and then by this expression we have the delta J as omega h also has to be less than 0. So if we're assuming one orientation if we assume an orientation such that omega h, the horizon frequency of the black hole, is positive, that means delta J, the angular momentum carried by this particle, also has that has to be negative. So this particle is not only carrying negative killing energy, it's also carrying angular momentum that's the opposite of that of the black hole. So it'll be spinning down the black hole. So this kind of explains where we're getting the energy from, right? We didn't just create energy for free. When this particle crosses the black hole horizon, it's going to carry negative energy and angular momentum. It's going to cause the black hole to spin less rapidly. So basically, the black hole is losing rotation energy, which will compensate the energy that the escaping particle will get.
And the mass of the black hole, it's also modified, right? Or not?
Yeah. So So like the new mass of the black hole should be basically m minus delta E. Or sorry, m plus delta E. Or, yeah. Yeah, so in class tomorrow, we'll actually discuss how this particular relation that we derived here for particles undergoing this Penrose process is actually a special case of the black hole area theorem, which is a theorem Hawking actually proved about governing what happens to the area of a black hole horizon after it undergoes some process. But I think I'll end here for today and answer any other questions y'all have.
Yes. So you are tapping like the angular momentum from the black hole. At some point, this angular momentum will be such that you won't have these orbits that enter the ergosphere, and then you cannot do the process anymore. You need like this A to be like such that you have orbits that enter the ergosphere, right?
Yeah, for this particular ones, where we looked at incoming parabolic orbits in infinity. You need a certain value of A to actually have these orbits enter the ergosphere. But in general, if you have a non-spinning black hole, then it will have a ergosphere, and there will be some way to extract rotational energy from that. So we'll talk about a lot of different ways to do that in the next couple of days.
Okay.
Any other questions? Okay. See you tomorrow at 9 a.m.